we're going to look at how to name decimals. First of all, let's just review. When we have whole numbers, we start with units, tens, hundreds, thousands, 10,000s, 100,000s. Now we're getting into lottery money here. Millions, even better. 10 millions, 100 millions, and finally billions. And to name these, we have 1 billion, 638 million, 975,000, and finally 482. Now remember what this really means. We can write this in expanded form in powers of 10. For example, the billion is 1 times a billion, 1 with 9 beautiful zeros after it. 600 million, and so forth, in decreasing powers of 10 until we finally hit 8 times 10, 80, and 2. Now remember, everything we can do in this form can also be expressed as powers of 10. 1 times 10 to the 9th, plus 6 times 10 to the 8th, and so forth in decreasing powers of 10 as we work from left to right. 8 times 10 to the first, and remember that if you have just a single unit, 2, anything times anything to the 0 power is equal to 1. So to continue our smooth progression from high powers of 10, 10 to the 9th, a billion, to how to represent any numbers from 1 to 9, you could multiply that by 10 to the 0 to keep that pattern going. And the pattern is the interesting part of this, because we'd like to keep this same kind of a pattern we have here going for numbers that are less than 1. Let's investigate this. For example, suppose we have the number 482 and 1/2. The 400 is 4 times 10 squared. The 8 is 8 times 10. The 2 is 2 times 1, or 2 times 10 to the 0. But all of a sudden, with that 1/2, we've lost the pattern. It certainly makes sense mathematically, but we'd like to keep our number system going so that we use the same ideas all the way through it. And what we're going to try to do here is find a way of representing that 1/2 that fits in the patterns that we've already established. And let me remind you, I'm expanding this number again. And what I ask is, how can I represent that 1/2 in terms of powers of 10? Let's look at an equivalent fraction. We spent a lot of times in the previous classes changing fractions to their lowest terms. Here, to make them fit within our decimal system, we're going to look at writing the equivalent fraction, but going the other way. I can write 1/2 as 5 over 10. And since it's expressed in terms of tens one way or another, maybe I can use that to integrate it into the system we're trying to develop. 482 and 1/2 is completely equivalent to 482 and 5/10. Let's look at the pattern here. I have 4 times 100 plus 8 times 10 plus 2 times 1 plus 5 times 1/10. You see, tens are still involved with that 5. So it's 4 times 100. Let's look at the pattern. 10, 1, 1/10. This is looking good. So I can say that we could represent numbers this way. You know, 1,000, 100, 10, 1. Then going the other way, we could, in terms of quantities less than 1, we can say 1/10, 1/100th, 1/1000th, and so on. Numbers greater than 1 go 10, 100, and so forth. Numbers less than 1 go by fractions of powers of 10. 1/10th, 1/100th, 1/1000th. And that's a way that we use to fit these numbers into our decimal system, that fit numbers that are less than 1 into our decimal system. 482 5/10. We can say it as we indicate it, and we use a shorthand notation instead of writing the 5/10, because that can get very unwieldy. 482 5/10 plus 6/100ths plus 7/1000ths, you know, that could be huge. That could go way out there. So we're looking for a mathematical shorthand for doing this. It's represented as 482.5, where the point, called the decimal point, separates numbers on the left that are greater than 1, numbers on the right less than 1. When you see the 0.5, you know the number immediately to the right is going to be less than 1, and in fact it's going to be represented as so many tenths. Let's extend this idea. We have 100, 10, 1, the decimal point, which tells us where we stop counting things greater than 1, where we start counting things less than 1, and that's going to be 1/10. Let's sneak up on the idea. What about 482 1/4? We'd like to represent that quarter as in that series. In other words, if I have a quarter, is it so many tenths plus so many hundredths plus so many thousandths, so that we can take the quarter and fit it nicely into that system that we talk about, the decimal system. Now, how do we find how to fit 1/4 into tenths, hundredths, thousandths, and so forth? We need to, of course, take that fraction, and to change it to an equivalent fraction, we need to multiply by the same thing in the numerator, the top, and the denominator, the bottom. So first thing I ask myself is, what can I multiply 4 by to get it to be tenths? 4 times what equals 10? Well, can't do that. What can I multiply 4 by to get hundredths? Well, I think about this and I say, well, gosh, 4 times something equal to 100. How about 25? Okay, 4 times 25 is 100. Then if I multiply 1/4 by 25 over 25, which is just 1, what I wind up with is 1/4 can be written as 25 100ths. Let's continue with that idea to see how we can separate that into A tenths and B hundredths. If I write 1/4 as 25 100ths, I can write it as 20 100ths plus 5 100ths, or 20 plus 5 100ths, as you see there. If you have a fraction like this that you've split apart, you can write that as 2 separate fractions. I can take 25 100ths and write that as 20 100ths plus 5 100ths. Perfectly legal. Of course, if the 20 plus 5 was in the denominator, I couldn't do that. But since it's up on the top in the numerator, if you remember our previous couple of classes, this is a perfectly legal thing to do. Now when I've done this, I see I have 20 over 100 for the first term. I notice that there's a common factor of 10 in that first term. If I have a 10 over 10, that's equal to 1. So I can express 1/4 as 2 over 10 plus 5 over 100. Remember that A, B, and C sequence where I have A over 10, B over 100, and so forth? So matching this to that sequence tells me that my A would be 2 and my B would be 5. looking at this again, in decreasing powers of 10, I have 4 times 100 plus 8 times 10 plus 2 times 1, now plus 2 times 1/10 plus 5 times 1/100th. Let me write that as a decimal, the same way I did for the previous case of a half. In this case, I have 482.25, and I can read this where the 0.2 comes from the 2 times 1/10, and the 5 out in that second term comes from 5 times 1/100th. And I would read this as 482 and 25 hundredths, because that's where we started from. 1/4, you saw I could change to the equivalent value of 25 1/100ths. And of course, in common use, most people say 482.25. But what they're really describing is that number of hundredths. Here's one more. 482, well, we're getting real used to that number, but now we have 482 and 1/8, even less. What we need to do again is express 1/8 as that combination of tenths, hundredths, thousandths, and so forth. Let's try that. Now I have to ask myself, what is the lowest thing that I can multiply 8 by for that denominator, the number on the bottom, to get tens, hundreds, thousands? I can try, can I multiply 8 by anything to get tens? Nope. What can I multiply 8 by, a nice big even number, to get hundreds? Nothing. But I can multiply 125 by 8 and I get 1,000. Now I can express 1/8 in terms of things that are powers of 10. And so 1/8 is equal to 125 1/1000ths. It's equivalent, well, because I've multiplied the numerator and denominator by exactly the same thing. Just as I did before, I'm going to try to break this up to see if I can't get A tenths, B hundredths, and so forth. And I find I can. I can factor, let's look at this again, let's look at this eighth carefully. I can factor a 100 out of top and bottom of that first fraction to get 1/10. I can factor a 10 out of the second, and the third term stays by itself. Simplifying this, I get 1/10 plus 2 1/100ths plus 5 1/1000ths. Now I can go after writing this as an equivalent decimal expression, but again, I want you to notice how this follows decreasing powers of 10 going from left to right. I have the 482, decimal point 125. Again, that fits our pattern. And I would read this as 482 and 125 thousandths. Let's try to collect what we know and look at naming decimals. Here we go. We have hundreds, tens, units, and then here's the decimal point, the divider between bigger than 1 and less than 1. Tenths, notice the th on the end of it. Hundredths, thousandths, 10,000ths, 100,000ths, and millionths. Millionths represent something divided into a million parts. So 1/1,000,000th of something isn't going to be very much of it. Let's look at how we would name decimals. 0.3. Since there's only a digit to the right of the decimal point, only one, we're talking about 3 times 1/10, or 3/10ths, and here's the fractional equivalent of that. 0.75. We would read that as 75 hundredths and would write it as 75 over 100 if I were writing this as a fraction. 0.456, 456 thousandths, or 456 over 1,000 as a fraction. 0.035. We have to be careful here because now you see we have 3 places after the decimal. That tells us it's thousandths. The 0, we have no tenths, so we have that 0 there as the placeholder, and we have 35 thousandths. This is a hard one, and it's 105 hundred thousandths. How do we know it's hundred thousandths? Put your finger at the decimal point and go tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, and your fingers out past the 5, and we would represent it as a fraction that way. And finally, here's another one. We would write that as 101 ten thousandths, and we would represent it as a decimal this way. Let's review this system for naming decimals. First, you look at whatever the largest number is in the decimal, and that goes on top of the fraction. Next, you count the number of decimal places. For example, here, I see that I have 3 decimal places. I put a 1, and then I write the number of zeros equal to the number of decimal places. So the fraction 123 1,000ths is equivalent to the decimal 0.123. Let's look at changing decimals to fractions. We've already talked about this a bit when we developed the idea of decimals. If I have 0.88, that's equivalent to the fraction 88 100ths. But it's not a fraction reduced to its lowest terms. So once we go from writing the decimal to a fraction in terms of tenths, hundredths, thousandths, let's reduce it to lowest terms. I can pull a 2 out of the numerator and denominator and get 44 fiftieths. I see that what I have is still divisible by 2. I can pull out another 2 from numerator and denominator, and I can't go any further than that because 25 and 22 have no other mutually divisible factors. I can say then that 0.88 is equivalent to the fraction 22 25ths once I've reduced it to its lowest terms. And this is the general procedure for changing decimals to fractions. What about going the other way, changing fractions to decimals? We need to represent the fraction in terms of a denominator with 10, 100, 1,000, and so forth, so we need to go for that. Here, for example, I have 5/8. What can I multiply 8 by to get 10? I can't think of anything. What about 100? Again, there's no whole number that I could multiply 8 by to get 100, but by the time I get to 1,000, I remember I can multiply 8 by 125. If I do that to the bottom, I need to do that to the top or the numerator, and I find that I can represent 5/8 as 625 1,000ths. Then by following the rules, 5/8 is equivalent to 0.625 as a decimal. Right now, we've only dealt with special cases where you can multiply the denominator by some whole number to get 10, 100, 1,000, but there's a general technique that we'll see later for changing any fraction into a decimal. Right now, though, we've seen that 5/8 is equivalent to 625 thousandths. How about placing decimals on the number line? This again works very similar to placing whole numbers on the number line, except we have to split things finer. 1.4 is equivalent to 1 4/10. On the number line, that's going to be somewhere between 1 and 2. Then we can take that interval between 1 and 2 and cut it up even finer. Cut that interval between 1 and 2 up into 10 pieces. Now we can find out exactly where 1.4 goes. This is like rulers. If you have a ruler, the better the ruler, the finer it gets, and the less estimating you have to do. If you look at a very, very good ruler, it's got lots of little lines, so it divides up the number line very finely. We can use the number line just as we did for whole numbers to determine which numbers are bigger or smaller than others. First of all, when you have decimals, 0.5 is 5/10, 0.50 is 50/100th, which reduces to 5/10, and so forth. So 0.5 is equivalent to 0.50 is equivalent to 0.500. What we get here is that adding zeros to the right of your decimal is not going to change its value. It's equivalent, and sometimes it's useful to do that when you want to compare decimals together. Let's compare these two numbers, 3.752 and 3.0752. First of all, I notice the number on the left has 3 decimal places. The number on the right has 4. If we want to, we can add a 0 to the right of the first number, so we have 2 numbers to 4 decimal places. Let's look at putting these numbers on the number line. Right away we can see those numbers are going to be between 3 and 4, so that we can develop a finer scale just for that interval. Let's look at putting first 3.0752. That's going to be pretty close to 3. It's 3 and 7/100ths and so on. So it goes there, between 3.0 and 3.1. 3.752 is going to go here somewhere above 3.75. We need to make the scale even finer to figure out exactly where. But we see that the 3.0752 lies to the left on the number line, therefore it's less. Or we could say equivalently, because it lies to the right, 3.752, and if I wanted to, I could say that 0 again is greater than 3.0752. Which of these is larger? Now, with negatives, remember, we have to be careful, because even though it might look right away that the minus 2.137 is going to be bigger because it looks like a larger number, we have to be careful. It's negative. We can add a 0 for the comparison if we want to, and we see that these numbers are going to lie between minus 2.2 on the number line and minus 2.1, going from lesser to greater. If we place the numbers, there's minus 2.1370. It's, again, we start at the 2.13 and work to the left because it's negative. We do the same thing with the second number, starting at minus 2.1 and working to the left. And we see that the minus 2.1370 being to the left is the smaller number on the number line when we're dealing with negatives. So that we can say minus 2.1037 is greater than, because it lies to the right on the number line, than minus 2.1370. Wow, you have to be careful here. Let's look now at rounding decimals. We'd like to round 3.175 to the nearest tenth. We do this very much the same way that we round decimal integers. We put our finger on the place that we want to round to. Then we check the next digit to the right to see whether that's greater than or equal to 5. If that's the case, then we round up. And when we do this, we say that just as we did with whole numbers, we change the 1 in the 10th place to a 2, and if you think about it, we can then add zeros for the other 2 places. But remember, when we're talking about decimals, quantities less than 10, adding zeros to the right doesn't change the value. So that when you round decimals, you drop any zeros to the right of the place you've rounded to. Here are the rules for rounding. You locate the digit to be rounded to, then look to the digits to the right. If it's greater than or equal to 5, you round up, change the number you have your finger on to the next highest number, and then throw away anything to the right of that. If it's less than 5, you don't change the number, and you don't have to put zeros in to the right, you just throw those zeros away.